In this lesson, we're going to learn how to draw Lewis structures, which are electron dot structures for molecules. These diagrams help us visualize how valence electrons are arranged in molecules and how atoms share electrons to form covalent bonds. Once the Lewis structure is drawn, it can then be used to determine molecular shape and polarity, which is key to determining a lot of physical properties. By the end of this lesson, you'll be able to confidently draw correct Lewis structures for simple molecules. So as we've already seen, when you have two nonmetals combining together, they share their electrons to form covalent bond. Now, as I may have mentioned in the previous lesson, rather than showing dots for the shared electrons, I prefer using a stick because first off, it's simpler to look at, and also you can say that you are sticking the atoms together, so it kind of helps with remember what's going on. In addition to being able to stick the atoms together to form the molecule, you also have to be sure to include any lone pairs that are present in your molecule because they have a big impact on the shape of the molecule. All right, so Lewis dot structures. Got kind of some leading questions to help you understand the process. So first question, what is the formula for water? First time I ask this to my students, they're like, this is a trick question. So hopefully you said to yourself, H2O. How many valence electrons does each hydrogen have? Well, it's in group 1, so therefore it has one valence electron. Each hydrogen has one. How many valence electrons does the oxygen have? Oxygen is in group 16, so it has 6. So how many valence electrons are there in total in a water molecule? So you say, well, we got 2 hydrogens and 1 oxygen, so therefore it would add up to 8. So let's do some more. It says how many valence electrons are in H2O2, which is hydrogen peroxide. So you see, all right, well, I have 2 hydrogens. Each hydrogen is 1. 2 oxygens. Each oxygen is 6. So it works out to be 14. Another example. How many valence electrons in H2SO4, which is sulfuric acid? So we kind of go through the same process. So we have 2 from the 2 hydrogens. Sulfur and oxygen all have 6 valence electrons because they're in the same family. So 6 times 5 is 30, so it would be 32. So there are 2 different levels of Lewis dot structures. There's the ones that I call simple Lewis dot structures, and these are the ones where you just kind of look at the electron dot structure of the central atom, and wherever there is an unpaired electron, you're going to pair it up with an unpaired electron on the terminal atoms, the other atoms that you're attaching to the central atom. The other ones, which are an expanded octet or hypervalent compounds, we'll talk about those in the next lesson. So the first step is to determine the central atom. The central atom is the one that's going to go in the middle. Everything else is going to be attached to it. So it ends up being the one, most typically, that you have the least number of. So water would be oxygen, BF3 would be boron, nitrogen trichloride would be nitrogen, C2H6, it would be the 2 carbons, but they're both going to go in the middle. And then we have silicon tetrafluoride would be silicon. So now we draw the electron dot structures. Going on across. And then wherever you see an unpaired electron, so we got one there. Each hydrogen has 1 unpaired electron. So that means we're going to form a bond on either side of the oxygen like that. Boron, same idea. Each fluorine has 1 unpaired electron. Nitrogen has 3, not nitrogen, chlorine. It's a halogen, so it has 1 unpaired electron. So again, they're going to match up with the number of unpaired electrons. So I said the carbons were going to go in the middle, and so we're going to let them share a pair. And then silicon is in group 14, has 4 unpaired electrons. So we go ahead and match everything up. I've got them color-coded just to make it a little bit easier to see what's going on. As you can see, this is why I don't like the dots for the shared pairs, because this is visually very, very noisy. It's hard to see what's going on. So the last step is to make sure that the number of valence electrons you are supposed to have is equal to the number of valence electrons you actually have. So we go through and we count 2, 4, 6, 8. So that's how many that water molecule has. We do the math, and yeah, we're supposed to have 8. Do the same thing for the BF3. Each fluorine has 8 around it now. 8 times 3 is 24. Do the math. So we got 3 from the boron plus 21 from the fluorines, gives us a total of 24 valence electrons are allowed. And then we just kind of finish it off. And the nice thing about the simple Lewis dot structures is that your valence electron count should always pretty much work out because we're just matching up unpaired electrons. There's nothing weird about what's going to happen. All right, so what do you do when you've matched things up according to your electron dot structure and you still have unpaired electrons? So let's do the Lewis structure for oxygen. They tried calling it dioxygen gas for a while, and that just didn't stick. So everybody just says oxygen gas instead of dioxygen. That's what it really ought to be. So we go through and say, all right, there's our electron dot structure for oxygen. There's the other one. We go ahead and we let them pair up. But the thing is, we still have these 2 unpaired electrons. In your Lewis structures, you will never end up with unpaired electrons. There are molecules that have unpaired electrons. They're called free radicals, but we're not going to do any of those because there's a whole set of rules that go with handling them. So all of your electrons will always be paired up. So what we're going to say is, well, instead of having them unpaired out here, we're going to let the oxygens share both pairs of electrons, and they end up making a double bond. Now here's where the sticks are really much more helpful. So we got, we're supposed to have 12 valence electrons, and we have 2, 4, 6, 8, 10, 12. So we have the right structure. And then another one that you should really commit to memory is nitrogen. So if you look at the 2 electron dot structures, we see that we have 3 unpaired electrons on both of them. The only thing they can do is pair with each other. We're not going to have any unpaired electrons. So this tells you right away that we're going to end up with a triple bond, which looks much better like that. And so we're going to check it. So nitrogen is in group 15, so we're going to have 5 valence electrons per nitrogen, so 10 total. So 2, 4, 6, 8, 10. So that's how we know that that is the proper structure. Now, a favorite question to ask on tests is, which of the diatomic elements has a double bond? Which one has a triple bond? You can either just draw them every single time or just commit to memory that oxygen's a double, nitrogen's a triple. And it's actually because of this triple bond in nitrogen that plants need nitrogen-fixing bacteria, or the assistance from them, in order to convert atmospheric nitrogen into the nitrates that are nutrients for the plants. Because the plants cannot directly break down that triple bond to make the nitrate compound. A triple bond is not quite 3 times stronger than a single bond, but it is stronger than a single bond. And remember, a stick is 2 electrons in a bond when you are counting electrons. All right, so there are 7 elements, like nitrogen and oxygen, that always come as a pair. And I kind of call it the Magnificent Seven after an old war movie or a muster, and I don't remember which now, that my dad always used to like to watch, called the Magnificent Seven. Anyway, so for the 7 diatomic elements, one of them is hydrogen, and there's its Lewis structure. The rest of the 7 start at element number 7, so nitrogen, and they make a 7. So the rest of the 7 go nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Astatine is probably also a diatomic element, just to fit in with the rest of the family, but then that would be 8 elements, and that wouldn't fit with the whole 7 thing. And astatine is one of the rarest naturally occurring elements, so nobody gets to do much chemistry with it anyway. So that's why it kind of gets left out. Notice all of the diatomic elements have single bonds, except for nitrogen and oxygen. Nitrogen has a triple, oxygen has a double. So hydrogen is just a stick and hydrogen's done. And for the three halogen gases, or three halogen elements, we're going four, I can count. They're all going to be satisfied, they're going to have their octet satisfied with 3 lone pairs around each atom. All right, so some guided practice. The assignment that goes with this lesson is called Feeling Dotty. And so first thing, you want to figure out the number of valence electrons. You cannot get around this. If you don't find the number of valence electrons, you're going to end up with the wrong structures, especially when we start talking about the ones with the expanded octets. Then you want to identify your central atom, draw the electron dot structure around the central atom, and then pair up the unpaired electrons with the unpaired electrons on the terminal atoms to make your Lewis structure. And then lastly, check your electron count. All right, so we got CH2F2. So the first thing we have to do is we have to add up our valence electrons. First thing I have to do is turn my pen on. So we have 4 from the carbon, a total of 2 from the 2 hydrogens. And then we have each fluorine is 7, so 14. So 18, so that's 20 valence electrons is how many we're supposed to have. The element that we have the smallest number of is carbon, so that's going to go in the middle. So there's my carbon, its electron dot structure. Now each hydrogen, I'm going to change colors, only has 1 valence electron. And as soon as you make a bond to hydrogen, it is going to be done. You don't have to add any more electrons to it. So I'm going to do a dot over here. Here's my hydrogen. Let's change colors. So there's 1 bond. I guess that works. Go back to black. And I'm just going to stick the other hydrogen electron up here. It doesn't matter where you put each one of these things. So there's the single bond that goes between the carbon and the hydrogen. Now each fluorine, go back to, let's do blue now. So remember the electron dot structure of fluorine. It's got those 3 pairs and then 1 unpaired electron. So we're going to have the unpaired electron, and that's going to get shared with the carbon. And they are going to make a single bond. And then we got the other fluorine. You think by now my handwriting would be better on this with this tablet. And there we go. So the Lewis structure is carbon in the middle, 4 sticks coming off of it, and then we got hydrogen, 2 hydrogens attached to it, and we have 2 fluorines attached to it, and each fluorine has 3 pairs on it. And that one I gave you the name. It's called methyl difluoride. Okay, so this one is, go back to red. I had to underline the carbon because we only have one atom of each type, so that I was trying to indicate what the central atom is. So we got to add up our valence electrons. So I have 1 from the hydrogen, plus 4 from the carbon, plus 5 from the nitrogen. So we're supposed to have 10. So I'm going to put carbon in the middle. And say, all right, well, I'm going to put my hydrogen off here because I know it's just going to get attached. And as soon as I make a bond, hydrogen is done. Now nitrogen, it's got that 1 pair on top, or not on top, but it has 1 lone pair, and it has 3 unpaired electrons. We have to bond these 2 together so that there are no unpaired electrons left. So this tells me, and hopefully you as well, that we are going to end up, these guys sticking off on the side here are going to end up being part of a triple bond. So we go 1, 2, 3. There's our nitrogen. So now we're going to check our valence electron count. And these are X's. I was crossing them out. So we have 2. Let me turn the laser pointer back off so you can see what I'm counting. 2, 4, 6, 8, 10. So that's how we know that that is the right structure. And the name for this, if you're following along with the feeling body assignment, I forgot to put it on it. The name for this compound is hydrogen cyanide. All right, so that's it for the simple Lewis structures. So just to wrap it up, Lewis structures show how the valence electrons are arranged around the central atom and how they get shared to form covalent bonds. Remember, a stick is 2 shared electrons, and that's the covalent bond. And then any electrons that are not in a covalent bond are going to be non-bonding electrons. They're also called lone pairs. Make sure you know how many valence electrons you're supposed to have in your structure before you draw it. There's a lot of people that draw the structure first and then tell me, oh, well, that's how many valence electrons it has. And if you're doing something other than a simple Lewis structure, you're going to end up with the wrong count. The central atom is the one that is usually the least common element. When in doubt, carbon goes in the center. It's just that kind of element. And then you'll form double and triple bonds whenever you have unpaired electrons left over, or you need to satisfy the octet on on the central atom or on the terminal atom by converting lone pairs into a double bond. We didn't see any examples like that. So that's it for simple Lewis structures. So next time we'll be talking about the extended octet, sometimes called hypervalent compounds. Thanks for listening.